So what we want to see here now is what should the maximum average power transfer? What do I need to do to get maximum average power transfer? So we're going to look through this quick example here to illustrate this, and then we'll do another example of finding it here. Now this is very similar to finding the maximum power transfer for resistors. And remember, for maximum power transfer, if we had just resistors, we had this R equivalent that we found, which we also called R Thevenin, and we wanted to set this equal to the load. That's the resistor we wanted to use for maximum power transfer. Now, here we're asking, okay, well, I want maximum power transfer as well, but what do I want here? If we want to think about it, is maximum power transfer, when we're talking AC, well, we have this complex power, and we've got average power and reactive power. And what would we really want to maximize? Well, remember, reactive power is real power, but we don't get to use it. It doesn't let us turn a crank. Average power is what lets us turn the crank. So we should try and shoot on getting the most average power delivered, because that means I'll be able to effectively have the most power in my system to turn the crank. And so I need to ask myself, what would I set the value here to be? Now, if we think about it a little bit, we might have a guess here. You might even guess initially, you might say, okay, well, I'm going to let my load equal the equivalent impedance. That might be your guess, and you're close, but you're not 100% correct. It's actually the conjugate of the equivalent impedance. And the reason is we want to try and get rid of that. We're not getting rid of the reactive power. It's still there, but we want to, quote, cancel the effect of it as much as possible. So I've got this capacitive effect going on here on the input. There's this capacitive thing. So what I want to do in order to get maximum average power transfer, I want to put an inductive load on here. So if your source is capacitive, you put an inductive load on. Where you can also kind of think of the opposite. If the source is inductive, you put a capacitive load on. Now, the reason for this, we'll see in a second. It's going to be, I think, very clear once we see this and we kind of go this. For this example here, this is a pretty easy example to see what the equivalent impedance is. I'm not even going to draw anything here. This equivalent impedance is just looking why I have this 1 ohm and this minus J2 in series. So my equivalent impedance is 1 minus J2 ohms. But what that means is I set the load to 1 plus J2 ohms. Now remember, if it's a positive imaginary, that means it's inductive. If it's negative imaginary, that means it's capacitive. So I've now put an inductive load on. But let's actually do the computation, and let's actually compute P for load. So if we redraw the circuit here, I'm just going to write this now as 60 volt RMS because it was at an angle of 0. I have 1 ohm minus J2 ohm, and then I'm going to put on a 1 ohm and a plus J2 ohm. Now this is a simple series circuit here, and if I do a loop here to compute the current, well, current again in this case would simply just be 60 divided by 1 minus J2 plus 1 plus J2. Now I'm putting these in parentheses to indicate this was kind of my source, and this here is my load. But notice what happens here. These imaginary portions cancel out, and I get 60 divided by 2, which is 30 amps. Now, what's really important to notice here is notice that the current is in phase with voltage source. So the current is in phase with the voltage source, which means if you're thinking about the voltage source here, that means it's delivering maximum average power, and that's because for the power factor for the voltage source. Now, we're not talking about the power factor for the loads and everything, because it's not that all the power getting delivered to the load is going to be an average power. There's still going to be reactive power. But if we think about what the power factor is for the source, since the voltage and current are in the same phase, that means theta V minus theta I is 0. So cosine of theta V minus theta I would be equal to 1. So I have a power factor of 1 for my source, which we know that's the best power factor you can possibly have. So that has to be where I get maximum average power transfer. Now that does not mean the power factor for these loads are going to be 1. That's just saying the source is delivering the maximum average power it can. And so let's go ahead and compute then what that is. Well, we have my current as 30 amps, which actually makes this computation for the complex power really easy, because it's my current squared, because we're in effective here. Maybe I should have emphasized this. Remember, it's the magnitude of I effective squared times the impedance. So this would be 30 squared times 1 plus J2, which 30 squared is 900, right? So this would be 900 plus J 1800 volt amp. So we're still definitely not getting all of my power on the load as being average power. We still have reactive power. In fact, the reactive power is twice as much as the average power. But if we look at what is the average power being delivered, it's 900 watts. So that's maximum average power transfer. Now, as a side note here, let's go ahead and do these things here. So we said power factor for the source is 1, because voltage and current are in phase. That's important to know. If your current and voltage are in phase, your power factor is going to be 1. All right, but now let's look at the power factor for load. Well, S, converting that to polar format, and I'm doing this real quickly on my calculator here. (2012) at an angle of 63.4 degrees. Now there's two ways you could compute this. You could compute this as 900 over 2012, but that's also just equal to the cosine of 63.4 degrees. And why is that the case? Remember that power triangle, and I'll draw it here. which is a power factor of 0.447. So the power factor for the load is 0.447, meaning the load is still got a lot of reactive power in it. But as far as the source goes, as far as for the source being able to deliver the maximum average power, the source's power factor is 1. Now, let's draw that triangle to see, again, why I could just do that cosine instead. So this is 63.14 degrees. Maybe not 100% accurate triangle here. Let me redraw this a little bit. Make it a little bit more accurate. (63.14 degrees). And this is 900 down here. This is 1800. And this is 2012 as far as our units go. And so we can see we did 9,000 over 212, but that's just cosine of 63.4 degrees. All right, so let's look at another example here. And I'm going to do almost the exact same example here, but I find that people make mistakes and they're not careful when looking at circuits and finding equivalent impedances. So for these next couple examples, we're just going to find ZL for max average power transfer. Find ZL for max average power transfer. So, we're looking at a circuit like this here. And I did this on purpose because it looks very similar to the previous example. And I see a lot of people just combining this in series. That's wrong. Remember, when you're finding equivalent things, you need to turn off your power supply, which a voltage source becomes a short. And so I would have this circuit. But remember here, I've got 3 wires connected at that node, 3 wires connected at that node. So this is not a series. These 2 components are not in series. And in fact, what we can do here is bend that resistor over 1 ohm resistor, and we can see the resistor and the capacitor are actually in parallel. And so ZEQ is equal to the parallel combination of these 2 components, which would be 1 times negative J2 over 1 minus J2, which is equal to, let me just do that computation real quickly. This is equal to 0.8 minus J.4 ohms. So we definitely still have a capacitive input here, a capacitive source. 0.8 minus J.4. But if that's my ZEQ, my ZL that I should be adding is the conjugate of this, which would be 0.8 plus J 0.4 ohms. So yeah, I'm absolutely still putting an inductive load on, but it is not what you might think. It is not putting a 1 ohm and a J2 ohm in series. It's actually putting a 0.8 ohm and a J.4 ohm inductor in series. So make sure you don't make a silly mistake on something like that. So that actually is going to wrap up our discussion on power for this module here. So there's quite a few things we've talked about, lots of formulas. Again, I'd encourage you to keep a separate sheet of paper with all the formulas written down on it, just as a reference, so that when you're doing the homework or quizzes, you have a nice handy reference for your formulas. Also, don't forget about the online calculator if your calculator that you have cannot do matrices with complex numbers. You have to buy a pretty fancy calculator. Some scientifics will do it, but like I have a TI-84 graphing calculator, it won't do complex numbers and matrices. So I just turn to that calculator online often. And remember, the link is on the Blackboard site for it.